Hello, everybody. I hope everybody had a good weekend. Practiced lots of stoichiometry, stayed safe, and that you are ready to begin talking about gas laws. We're going to be doing Chapter 7 today. Not the whole thing, but probably most of it. Chapter 7 through 10 are not that long, and pretty much it's going to be like 1.5 lectures to do each of them, and then we're done. Yeah, that's it. So we're in the home stretch now. That means a lot of quizzes are going to be coming up pretty quickly, so make sure that you are reviewing the material, staying on top of it, because that exam number 2 and then the final exam will come up faster than you think. Blink and you'll miss it. Speaking of which, Chapter 6 quiz number 6 is due on Thursday. Make sure you get that in by the deadline. There is no lab due this week, but tomorrow I will be presenting a lab lecture where we will go over worksheet number 4, which involves 2 topics that we don't really get to talk about in this class just due to the time crunch. One of them we mentioned a little bit, the other one we just totally don't. But they're both pretty relevant to the nursing and medical profession, so we'll talk about that tomorrow. But for today, we're going to talk about gases. We have talked about... we've talked about solids and liquids and gases very briefly at the very beginning of the quarter. We mentioned a little bit about how, we can make solutions out of stuff. That's a thing that we can do. We're going to spend Chapter 8 doing the liquid phase with solids dissolved in it, mostly. And then Chapter 7 is going to be just the gases. And then we don't really study solids in this class. Anyway, what we're going to do the first 7 sections, which will not take very long, and then we'll probably dip into evaporation and boiling, and then intermolecular forces is the more important one. We'll spend Thursday doing that. All right. So the first thing we want to do is we need to talk about what gases actually are. And that follows this theory called the kinetic theory of matter. And so what gases in a box would look like would be something like this. So let me get the diagram here. Oh, that's not very... Let's just do this. I didn't capture all of them. That was silly of me. Alright, so, oops, that didn't work on my screen. There we go. Okay. Where can I write? I can write right there. Okay. So if I have a container, and inside the container are my particles of gas, they don't just sit here and hover in place. What they end up doing is they bounce all over. Whee! Maybe this guy bounces into this thing and then goes like that. And this one just hits this wall. And this one's just going on its way. In our gas, all the particles are moving at all times. In any gas, all the particles are moving at all times. Anything that is moving has what we call kinetic energy. Kinetics is the energy of motion. Now, you could feel this energy of motion if you throw something at another person and then they catch it, or they throw it at you, or whatever. If you throw a basketball or a football, those are generally really light. They weigh like maybe a pound. And so you throw that, and when you catch it, you feel some impact on your hand, and it's not that much. Now imagine if you replace that with a bowling ball that weighs 14 pounds, and you tried to catch that in the same way. It would hit you with a lot more force because the object is really heavy. Likewise, you could increase the kinetic energy of an object by just throwing it faster. If you throw a tennis ball at the wall and it bounces off, it will make a sound, and the sound represents how much energy. Now, if you took a tennis racket and hit the same ball into the same wall, you would hit it with a lot more force than you could potentially throw it, presumably, if you weren't like a baseball thrower or something. And it would hit the wall with more sound, and there would be more impact. So kinetic energy is the relationship of mass and velocity. And I don't know, just in case you're curious, so kinetic energy There is a formula for it where we care about its mass and we care about its velocity, it being the object that is moving. And the more of either of those it has, the more energy it has. I know math scares you guys, though, so I'm going to just erase this. Now, what if we have a solid? In a solid, all of my particles just kind of bunch together, right? They're all stuck. Since the particles are not moving, they don't have kinetic energy. Their velocity is 0. But they aren't entirely stationary. What solid particles try and do is they wiggle. They vibrate, and they try and free themselves, but because they're stuck there, they can't do that. So we'll say they have some vibration. Now, what is keeping these guys stuck here? Well, in something like an ionic compound, that would look something like this. That's just a set of ions here. And these guys would be attracted to each other through some sort of bonds. Now, an attraction from a bond represents energy that needs to be overcome in order to free it. We call this potential energy. I don't know what happened with the R there, but that's okay. So potential energy is the energy based on the position of things due to some condition that they might have. For example, if I grab my phone and it's sitting on the table right now, and if I lift it up above, say, my head, in its state in my hand in the air, it is not moving, so it does not have any kinetic energy, but it does have potential energy. That is because I have separated it from the ground. I have given it energy to lift it up. If I were to let it go, it would hit the table, and that potential energy would then be converted to kinetic energy, which is why it starts moving. It moves towards the table, and then it hits the table. When it hits the table, the kinetic energy is then turned into other energy, which would be like sound and vibrations and temperature and heat and stuff like that. So potential energy can be based on where something is relative to something else. In atoms and ions, when the atoms are next to each other and they form a covalent bond, or if ions are next to each other and they form an electrostatic ionic bond, those things are held together and they don't want to move from that spot. They will move if you overcome their potential energy. You have to provide enough potential energy to get them out of there. So potential energy is the energy that needs to be overcome in order to break these things free. Now, we've done the two extremes. We have gas and solids. So in the middle, we'll have liquids. And liquids are irregular. And what they end up doing is they just sort of move around freely within a confined space. And so they might move like this. And they just move all over the place. Now, what they don't do is this. They don't escape, at least not often. We'll talk about what happens when they do occasionally escape later on. But for the most part, they have some freedom, but they're still stuck together. So what we would say is that they have some motion, or in other words, some kinetic energy. But because they are held together loosely, they have some potential energy also. So that's the kinetic theory of matter. The kinetic theory of matter states that, hey, there's energy. It can either be energy of motion, or it can be energy based on some sort of bond interaction. We're going to call the motion energy kinetic energy, and the energy of position or relativity to other things, we'll call that potential energy. Oops. And any molecule that has lots of kinetic energy will move a lot. Any molecule that has very low kinetic energy must be stuck, and that would be because they have high potential energy. They're bound in place by bonds or something like that. And so we've got the three phases here, and we've already described these phases in terms of their kinetic energy and their potential energy. Solids have high potential energy but low kinetic energy. Gases have low potential energy but high kinetic energy. And in a liquid, it's roughly the same. There's about an equal magnitude of both. There you go. That was the first section. So, in Chapter 7, we're going to primarily focus on gases. And what that means is that we're going to be looking at particles that are bouncing around in a container. And that container could be open or it could be closed. We're going to stick with closed for the most part. Kind of like if you took a deep breath and then you just closed your mouth and just held your breath. The air in your lungs would be in a closed container, and it would bounce around. And it would hit the walls of the container, which would be your... Is it areolae? I don't know my biology very well, or anatomy at all. But it hits the receptors where it can dissolve into your bloodstream, and the CO2 will come out, and all that stuff just kind of bounces around in the interim. But depending on what you do with your gases, they can exert different properties. And we're going to analyze all of those properties today. So the first thing we want to do is we want to try and identify what properties that we can measure for a gas easily. Now what I need to do is I need to not delete everything. I want to keep this one. Alright, so let's see here. Oh, I don't know why this doesn't work all the time. Oh, Photoshop, why are you the worst sometimes? Alright. So on my diagram here, it's not going to let me drop there because I got to do that. Okay. On my diagram here, I have a bunch of molecules moving around. And there are some properties that I can identify about this gas to define it. The first that we're going to define is, what the hell is that? There we go. The first that we're going to define is the space that the gas is contained in, and we're going to call that volume. And that's the space the gas occupies. Now, the volume of the container is the volume of the gas by definition. The gas is going to move and expand to fill the entire container. The next thing that we're going to identify is this right here. When molecules strike the wall, they impact it and exert a force. When they do that, that force can be felt on the sides of the container. And if you have too much of that force, the container will rupture. And this force is known as pressure. And pressure is the force that the container feels based on how many collisions hit it per unit time. Now, if you make the container bigger, you have the same number of molecules hitting a larger space, which means that pressure goes down. But if you make the container smaller, then you have the same number of molecules hitting a smaller amount of space, and the pressure goes up. So pressure is going to be related to how big the container is. The next thing we need to consider is how fast the molecules are going relative to each other. If the length of my arrow represents how fast the molecule is moving, then the one with the longer arrow is going way faster than the one with the shorter arrow. Molecules that move faster have more energy, and thus we need to be able to understand what that means. And so this is called temperature, which you've probably seen before. Temperature is directly related to how fast the molecules are going, assuming they are all the same mass. Temperature and kinetic energy are actually the same thing. We measure the kinetic energy of molecules as temperature. So if you go outside and it feels hot, or the air feels hot anyway, that's because the molecules that are hitting you faster on average than slow molecules are, and they're transferring that extra energy that they have to you. If you go outside and it's cold, the molecules are moving slower, and what happens when they hit your body is that they gain energy. They gain your energy, and so you feel cold. The last property that we can measure is simply how much gas is in there in terms of how many pieces or particles. And that's pretty straightforward. It's just the number. Since we've been counting everything in this class so far in moles, we're going to continue to do that here. So these four things are the properties of our gases: temperature, volume, pressure, and number. These are all things that we can control. If you want to change the temperature, you just heat it up or put it in an icebox or something like that. You want to change the volume, well, you just expand the piston or contract the piston or something like that. If you want to change the number, you just put more things in or less things. And then finally, if you want to change the pressure, you could do any of those things and it'll change the pressure. So there's our definitions for those four things on the slides. Hopefully you've been reading along with those as we did that little diagram. Now, we do want to define some of these terms a little bit more. Let's talk about pressure a little bit. If you go outside and it's a windy day, what you end up feeling is the force of air buffeting you around. It will push you in a given direction if the wind is strong enough. The reason that you feel this is because the wind is exerting a pressure on you and pushing you in a given direction. It's the direction the molecules are moving. Now, if the air was perfectly still, what that would mean is that it would be at equilibrium around you. There wouldn't be any wind, but the molecules would still be moving. The molecules that are around you in the air are subject to all external forces. One of those is gravity. And if you were to draw a 1 square meter column that went from the surface of the ground all the way up to the edge of the atmosphere, it would have a tremendous mass that pushes down upon everything below it, which would be you. That mass of air is about 10,000 kilograms, which is a lot of mass. So if somebody tells you, "Do you even lift, bro?" you can say, yeah, 10,000 kilograms every second. Because I'm carrying the weight of the atmosphere on my very shoulders. And you are. Our bodies have acclimated to this. In fact, if we didn't have that pressure pushing down on us, weird things would start to happen. And if we have too much pressure pushing down on us, then weird things also start to happen. For instance, your blood will start to Any of the gases that are in your blood will start to evaporate or boil if the pressure is too low, for example. Or if you're exposed to too high of a pressure and then you change the pressure so much. That's known as the bends, and we'll talk a little bit about how you can get the bends and why you don't want that when we talk a little bit about pressure relative to the surface. Now, all these particles are being pulled down. What that means is that their weight will push down and will be felt by anything at the surface. If I were to draw a diagram of this, like so, let me get this, we'll save that for later. If I were to draw a diagram, let's suppose that we have, like, say, here's the Earth. And maybe over here, oops, maybe this is the sea. And I'm going to stand right here at sea level. Up above us is the atmosphere. And all of the air that is above us will push down. And that force will be a pressure. We're going to call this pressure atmospheric pressure. And we're going to use that as our unit. How many atmospheres are above you? Well, one of them, the one that we have. So if you are experiencing that level of force pushed on you, in other words, what you're feeling right now, anxiety about the pandemic and the class and other things aside, not that pressure, we can't measure that in atmospheres, but air pressure that's pushing down on you, that is about 1 atm. Now, if you have been somewhere that isn't sea level, you've probably experienced different effects. For instance, we live in Washington, so there are lots of mountains around. And let's suppose that you went to the mountains. Let me try him again. There we go. All right, so now I'm in the mountains. It's beautiful up here. You should join me sometime. What pressure pushes down on you here? Is the pressure in the mountains the same as the pressure at sea level? If you had to give it a number, based on my diagram here, you would say, oh, well, it's way smaller than it must be at sea level. And relatively speaking, it turns out that it is not that much smaller, but it is smaller. The reason for that is there's less atmosphere on top. If you go up to Denver, Denver is like 5,000 or so feet elevation. It's called the Mile High City for a reason. If you go up to that level of elevation, there is significantly less air above you. And so the amount of pressure that you feel at that location is reduced. If you have ever gone flying in an airplane, so here's my airplane here. The same thing is true. There is not as much air pressure pushing down on you when you are in the airplane. And the cabin pressure that you feel is artificial. Extra air is put in there, and then it slowly acclimates to the outside. What you feel when you do that in your ears is that they pop. And there's a reason for that, too. So if this is your ear, maybe you're like an elf, and here's your elven ear. And here's the inside of your ear, and here's the eardrum. Past the eardrum is the inner ear, and the inner ear has air in it. And so we'll say that here's the air at the ground. So this is 1 atm. Then you fly up, and now you are in a location where there is less air pressure. What ends up happening is that, there's more pressure on the outside of your ear. Or, I'm sorry, more pressure on the inside of your ear than the outside. And so what your eardrum does is it bulges in this direction while molecules move to equalize. And the result is your ears feel like there's a bubble in them, and you have to go, you have to gnash your teeth and chew gum or do something so that it equalizes. Because once it equalizes, and now it's not 1 atm anymore, once it equalizes, your ears feel normal. And then when the plane starts to descend, the air pressure builds back up, back to normal, outside, and now the air wants to go back in, and it feels like you have a bubble in your ear again, and you get to do the thing again to try and pop your ears. So these are all applications of air pressure. Later on, when we talk about boiling, and how boiling is related to the pressure of the gas above it, the gas being the atmosphere, we're going to revisit this picture. But for now, the amount of atmospheric pressure that you feel is relative to where you are in position to the edge of the atmosphere for the planet. Generally speaking, we use sea level as our definition for 1 atm. If you are higher up in elevation, you would experience a pressure of less than 1 atm because there's just less air above you. Nobody mentioned that I was drawing behind the picture here, sorry. Because y'all are so quiet. There we go. If you are at a higher elevation, there is less air above you, so the pressure is lower. And if for some reason you went to a lower elevation, like say, I don't know, you went to Death Valley or something. Here's Death Valley. Then the pressure you would feel on you would be higher than 1 atm. The same thing would be true if you went diving underwater. So if you're down here and you have a scuba tank, so we'll give this guy goggles just so that he doesn't die. Then the pressure you would feel would be from the air and then also from the water. Because water is way denser than air, water is much better at generating a pressure. And again, using the ear example, if you've ever dove to the bottom of like a 10-foot pool, you start to feel pressure on your ears because the pressure from the water is just really, 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 really high relative to the air. And so it's hard to dive down very far before the pressure starts to hurt your ears. All right, so again, that's what atmospheric pressure is, and that's how we define it. Any questions, let me know in the chat. Yeah, it says people are here. There are 9 people watching right now. Okay, you're just quiet, that's all. We've already talked about all that. Here are the units of pressure that exist beyond this course. We're only going to use 2 of these units. The first one is atmospheres. So we're going to use that a lot. The other one that you're going to see is torr. And the reason that torr is important is because a torr is the same thing as what is known as a millimeter of mercury. And when you take somebody's blood pressure, you measure their blood pressure in millimeters of mercury. So if somebody had a blood pressure of 760, that would be atmospheric pressure. Obviously, nobody's heart has a blood pressure of 760. Like, you would immediately die. Like, all of your cells would explode. It would be a very gory death. In fact, if your blood pressure gets like even close to like 160 or 170, I want to say, like, that's really, really awful. I think mine's like, what, 120, 110, something like that. I have low blood pressure. It's very strange considering all the salt that I eat. But anyway, that unit will be common enough that we're going to use it. And in one ATM, there are 760 torr. If you go into, like, say, mechanics or something like that, and you deal with gas pressures within, say, a tire, PSI is very common. That's the American unit that's used for pressure. 1 atmosphere is about 15 PSI. When you put air into your tire, it's important to note that the number that it tells you is not the pressure that's inside. It's the pressure that's inside plus atmospheric pressure. Because if your tire was flat and it had a gauge reading of 0, what is inside your tire is not a vacuum. All of the air has not been sucked out because you blew a tire. What that means is that the pressure inside your tire and outside your tire is the same, and so it reads it as 0. On a gauge pressure, the atmosphere is already subtracted out. So if you put a gauge pressure sensor onto your tire, it might say, oh, there's 2 atmospheres of pressure in here. But in reality, there's 2 from the air that you pumped in, and then 1 from the atmospheric pressure that's outside and was also inside before it was filled. So just keep that in mind if you're looking at pressure on gauges and stuff for tires, because gauge pressure and atmospheric pressure are different. All right, so now that we talked about pressure, we can actually show how pressure behaves. We're going to do that with some video demos here. But first, I want to draw a picture of this so that we can try and make a prediction about it. I've used up my entire pad, so let's just go that. All right. So for demo number 1, I'm going to have a balloon. Here's my balloon. And I'm going to trap my balloon in a box. And that box is going to be connected to a vacuum pump, which is just going to pump the air in or out, depending on which way I throw the switch. Now inside the balloon are gas molecules. And outside the balloon are also gas molecules. And they bounce around and hit the balloon, and they hit the container, and so on and so forth. What I'm going to do is I'm going to zoom in on this region right here and try and redraw it. So this is the boundary of my balloon. And here are my particles that are striking the surface of my balloon. On the outside, they push inward, and on the inside, they push outward. And if the particles on the inside and the outside push equally, so P exterior equals P interior, then the balloon stays where it is. But let's suppose that I did this. I'm going to turn the vacuum on, and I'm going to remove some of the particles from the outside. What would then happen to the boundary of the balloon? Type in the chat, what do you think the balloon would do? Would it expand or would it contract? Or would nothing happen? This is just my test to make sure the chat is working. There we go. People are talking, so that's good. So the balloon should expand under these conditions. So if I remove the external pressure, the balloon should expand. Let's see if you are right. So what that means that I need to do... I gotta call up the window, first of all. And then I need to... Is it this one? Yeah, but it's way too big, so hold on. I don't know where the boundary is for this video. So I'm just sort of guessing here. Oh, the other thing I need to do is make it... Oh, no. I don't want that. I gotta make this smaller. There we go. That's what I want. I'm a little off-center here, but... There we go. That's what I want. Alright. I don't know why that got small. Just gonna see a bunch of Final Fantasy music recommendations here. Alright, is it going? There it goes. Okay. So here we have this balloon. And what's going to happen is that the air is going to get sucked out through this tube. And when it does that, this happens to the balloon. I don't know if we have audio here. Oh, it's just somebody talking. We don't care about that. And you can keep doing this, and eventually the balloon will become the size of the container. And then when you let the air back in, this happens. Now the pressure on the outside is increasing. Now you could do this with anything that has air inside of it, such as this peep. And now it's alive! And then you put the air back in and it gets really sad. And now it's just kind of like, oh. Finally, they do this with shaving cream. And shaving cream has bubbles in it. If you remove the pressure, those bubbles expand, and the shaving cream itself expands. And it will get bigger and bigger. And, oh dear. Oh no, it's too big. Oh, it has touched the ceiling. Everything is over. The end. Alright. So, what did we learn from this video? Other than shaving cream and peeps have air in them. So, to express what we discovered mathematically here, we would note the following facts. So the first thing we would note is that as the pressure outside increased, or actually, let's not do increase first, let's do decrease. As the pressure on the outside right here decreased, what happened to the volume of the balloon? When I removed the air pressure on the outside, the volume got... This is where you say a word. What happened to the volume? It got bigger. There you go. It increased. Very good. And then as we put the air pressure back in and the pressure increased, what happened to its volume? It being the balloon. Now it decreased. Good. So the relationship that we have concluded here is that pressure and volume have an inverse relationship. And the way to represent an inverse relationship is by the following. You multiply them together and they equal a constant. What is K? K is a constant that is unique based on what situation you have. So if it's a balloon, it'll have some K. If it's like a piston, it'll have some K. If it's a balloon made of a different material, it'll have a different K. Every setup for your gas law will have some constant K associated with it. Now, the only thing that we really care about is that because K is a constant, that means that the pressure and the volume must be related to each other in this manner. So if, like, say K was 100 and P was 1, then V would be 100. But if P became 2, then or in other words, I doubled the pressure, I would have to cut the volume in half so that it would equal the same K. So if you double one, you have to cut the other in half. And if you triple one, you'd have to cut the other one by a third, because they have to multiply together to give you the same constant every time. That's why it's a constant. So that's what these slides are going to do right here. Where are my slides? There they are. The formula must be on a later page. Okay. And again, that's an inverse relationship, where if one goes up, the other has to go down. Now, why do we care about Boyles Law? Well, if you are in the field of medicine, which I suspect many of you are, this is the premise behind how syringes work. When you have a syringe and you pull the plunger up, you create a vacuum. So this space in here will have nothing in it. There's no air because the plunger was initially all the way at the bottom. When you do that, there is less pressure in this space than there is in the head space above this liquid. And so what this tries to do is it equalizes the pressure by pushing down on the liquid, which then goes up the syringe and fills it up. So if it weren't for Boyles Law, syringes wouldn't work, and you'd have to find another way to deliver stuff to patients. Probably like just drip IVs forever, which would be kind of miserable. And again, here's the formula for Boyles Law. But I've changed Boyles Law slightly, as you can see on the slide. And let's talk about what this means. Because that constant stuff that we have isn't super useful to us, we're going to redefine the formula. Earlier, I said that I could choose a number for P, and V would be an appropriate value to make K constant. In other words, if I had some initial volume and pressure, it would equal my constant. If I changed the volume, and the pressure changed with it, or the other way around, the result would still be this constant. Well, if something equals the constant, something else equals the constant, then they must equal each other. And what this means is that I can figure out, for any combination of pressure and volume, what a later pressure will be given a desired volume. And so we're going to do a few problems to figure that out. So for instance, here's a problem that's on the slides here. That didn't drag. There we go. Suppose that you have a sealed syringe with 10 milliliters of air in it, and inside it is at 1 atmosphere of pressure. If you pull on the syringe so that its volume is now 20 milliliters, what will the pressure be in the syringe? Whenever I do problems that involve these sorts of measurements, here's what I recommend that you do. We're going to make a table, and we're going to put all the information in it. So we're going to have a pressure and a volume, and a 1 and a 2. And we're just going to do this. And so now what you do is you just look for the numbers in the problem and put them where they should go. Whenever you see the number 1, 1 is going to stand for the before state. 2 is going to stand for the after state. So you have initial conditions, and then you do some change, and then you'll have the later conditions after you did the change. So let's fill in the numbers. P1 is the initial pressure, and that was reported to be 1 atm. V1 is the initial volume, and that was reported to be 10 milliliters. Then it says the volume has changed to 20 milliliters, so that must be the volume after. And then what will be the pressure inside the syringe in ATM? So this is the last thing that I need because I'm in the P2 column. And I don't have that number. So I'm going to set up my equation and solve for that variable. I want to solve for P2, so I'm going to divide both sides by V2 so that these cancel out, which means I can erase them. And now that I've solved for P2, I can then do the numbers. P1 was 1 atmosphere. V1 was 10 milliliters. And V2 was 20 milliliters. And there you go. So the pressure inside the syringe must be half an atmosphere, which makes sense because we doubled the volume. If you've ever done this experiment, maybe you have like an empty syringe at home that you use for, I don't know, like maybe cooking or something, or maybe you have to use it to like wash stuff out or whatever, I don't know. If you put your thumb on the end of it and then try and pull the plunger, it gets really hard to pull the plunger after a little bit, and that's because the pressure inside is very, very low, and the atmosphere is actually pushing your hand in to the plunger to fill in the vacuum that you were creating. All right, so that is Boyle's Law in action. Any questions about Boyle's Law? All right, the next one we're going to do is Charles' Law, which is volume and temperature. So we got to go back to, we'll put this on the screen here because we're going to come back to that in a second. And so now what we got to do, so I got to clear everything. And we got to draw the balloon again. Here's my balloon. Here are my air particles in the balloon that are bouncing off the sides here. And they are all moving at a certain speed. And when they impact the container, they transfer the energy to the side of the container, which keeps it at its given shape. But now let's suppose that we did the following. I'm going to make everything slower by reducing its temperature. So in other words, I'm going to put this in a cold bath. What happens to the pressure felt by the sides of the balloon, and thus the volume of the balloon, if I were to cool down all of the particles, so I make them go like half as fast? What would happen to the volume? Would it get bigger or smaller? Ooh, excuse me. It would get smaller. Good. Let's see if that checks out. So I have a balloon. And what we're going to do is we're going to pour... Oh, I have the wrong window for that. Hold on just a second. Apparently I had 2 windows going. Okay. I gotta clear one of those out so that I don't get confused here. Here we go. We're going to pour liquid nitrogen on a balloon. This is liquid nitrogen, and it is a temperature of... I want to say it's like minus 190 degrees Celsius. It's very, very cold. As a result, pouring liquid nitrogen on the balloon causes the molecules inside to get really, 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 really cold, and thus go really, 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 really slow. And then what happened to the volume of the balloon? Well, it got small. And it looks kind of sad now. But what we're going to do now is we're going to let the air inside slowly warm back up to room temperature. What will happen to the balloon as it does that? Well, let's find out. It's alive once more. So, by changing the temperature, we can change the volume of the balloon. So the relationship that we determined here was the following. That's not a pen. There we go. As T decreases, volume also decreases. And as T increases, volume also increases. So we call this a direct relationship. And the formula for that I was going to write the inverse. Let's write it the other way here. Is this. So if volume doubles, the temperature must double, and so on. Now, the way that we're going to see this more often is we're going to divide T over here, and we're going to get this. Because I could do the same thing over here. It's not 1. That I did before. And then we just get out the middleman, and we say that those two things equal each other. And so there's Charles' law there. So we can use Charles' law in exactly the same way to do calculations like we did Boyles' law. Now, the only caveat here is that when we do Charles' law and we use temperature, the temperature has to be in a value that cannot be 0, which means that we have to use that temperature scale that we introduced a long time ago. T has to be in Kelvin. Because if you put 0 degrees Celsius on the back of, or the bottom of an equation, you're dividing by 0, and you cannot do that. You don't get an answer that's a number. You get an undefined result. But Kelvin can't be 0, because that's the bottom of the scale, and we can't get there. So, all your temperatures must be in Kelvin. And remember that the formula for Kelvin to Celsius is whatever your temperature is in Celsius plus 273.15. Now, I might give you the temperature in Kelvin, or I might give it to you in Celsius. So you're going to have to determine what you need to do based on what the problem says in the description. So let's do this example problem together. And so I have a balloon with volume 1 liter at temperature 298. What temperature must I heat it to reach a volume of 1.5? So just like before, I'm going to do this. And we'll collect our information. The initial volume was 1 liter. I want it to get to 1.5 liters. And the initial temperature was 298. So I gotta solve for T2. And remember, we don't want to move the V2 off of the other side because we'll get 1 over T2. That's not correct. If I have something that is on the denominator, remember, I got to multiply it up to get it on the top here. So I'm going to multiply both sides by T2 to move this up here. And now I can divide both sides by V1 and multiply both sides by T1 to get the actual formula that we want to manipulate. And now I just plug in the numbers. So the final volume was 1.50 liters. The initial temperature was 298 Kelvin. And the initial volume was 1 liter. The volumes cancel out, leaving Kelvin. And I get, it's going to be like 448 or something. 447. So you have to heat this up quite a bit in order to get its volume to increase just 50%. All right, so that's Charles' law. And there is one more law that we'll do before we take our break, and that's called, I want to say it's Avogadro's law. I don't know what the name of this one is, but it's volume versus number. And this one is a demo that I can do on my own. So I don't have a video. I also don't have a camera pointed at me, so it kind of loses the impact. But we'll draw it on the screen here. So I have a balloon right here, and I don't have any air in the balloon right now. And what I'm going to do is I'm going to inflate the balloon. Okay, ready? It didn't work. Hold on. There we go. By inflating the balloon, I put more gas inside it. What happened to its volume? So as N increased, there's more molecules of air in the balloon. What happened to the volume? The volume went Did it go down? Yeah, it got bigger, right? So I made a bigger balloon. It's hard to tell because I'm drawing it on the screen, I realize. I'm not actually doing this in class here. And then I can do the opposite. If I remove the air from the balloon, what happens to its volume? It gets small again. So this is a direct relationship also. And so we could write this as V equals K times N. And we could do the same thing with it, but the whole point that we're doing this for N is that we're going to introduce another equation after the break, where we just take these three relationships and we put them together. Oops, wrong arrow. So we'll come back to doing that in a little bit. After the break, we're going to talk about what happens when we combine Boyles' law and Charles's law together to get the combined gas law. We'll do that after our break. Let's go to the title card. Let's do... I do have a timer on screen, so I can do that. All right. So I'll turn the music back on. And we'll take a 10-minute break. Let's start the timer here. And I'll see you in a bit. Boo. One of these days I might actually get it on 10. Who knows? Oh, I forgot to pull the mic out of the thing. There you go. Oops. Hold on just a second. Boop, boop. All right, welcome back. We're going to continue by talking about the combined gas law, which is basically just the same as what we did with the other two gas laws, except there are more variables. And so you'll need to choose this formula when you seem to have all three things that you want to put numbers in for: pressure, volume, and temperature. All right. So here's a sample problem that would use the combined gas law. And just like before, well, we go back here. That's the wrong button. There we go. We go back here to work on our problem. We're going to make a table that just has all the variables in it. Actually, I could just do that. So for the combined gas law, I have a P, a V, and a T. And then I have before and then after. And then there's the formula. And so now all I had to do is figure out where the numbers go and then calculate the answer. So what I want you to do, since you've seen 2 of these before and this is just the new one, I want you to try and solve this problem and solve for the variable that is missing. So type your answer in the chat when you get the correct answer, and we'll go over the answer in just a second. So I'll see you in a bit. How are we doing? Any questions so far? Have we got the answer? Do you want more time to work on this, or should we go over the answer? What would you like me to do? Not you, Maya. I know what you want to do. My cat's trying to jump in my lap. We can go over it together. That's fine. Oh, I'm already on that screen. Okay, so what we got to do is we got to plug in the numbers first. We got to figure out what the numbers are. So I have a balloon, and the balloon has oxygen in it, so that's a gas. And it has some volume and some pressure and some temperature. And then I move the balloon somewhere else. And here's its new temperature, and here's its new pressure. So in the problem statement, some of those numbers are before and some of them are after. And so what we have to do is identify which is which. So the 2.26 liters, the 1 ATM and 298K, that must be after I did something to it, which was move the balloon. So the volume initial for volume 1 should be 2.26 liters. Its initial pressure is 1 atmosphere. And its initial temperature is 298 Kelvin. And then after I've moved it, its pressure changed to this, 0.835 ATM. That dot's a little tiny. What do I have? V2 is what I'm solving for because I didn't give a second volume. And the temperature is 265 after I've moved it. So you got a V2 bigger than V1, but the temperature went down. So that can happen in these problems because not only is the temperature going down, but also the pressure is going down. And so they both work against each other. So one is making it bigger and the other one's making it smaller, and it's just a matter of which one has a bigger impact. So you do have to consider them both together. If you had the pressure went up and the temperature went down and it got bigger, that would mean you made a mistake in putting in the numbers. But if one can make it bigger and one can make it smaller, then it can go either way. And that's totally normal. I'm going to solve for V2, which means that I need to multiply both sides by T2 to cancel them out on the right. And then I divide both sides by P2 to get V2 by itself. So V2 is equal to T2 P1 V1 T1 P2. I just switched the order of these two so that they line up a little better. Now I can't see my numbers, so I gotta scroll this back up. So T2 was 265 Kelvin. P1 was 1 atmosphere. V1 was 2.26 liters. T1 was 298. And P2 was 0.835 atmospheres. Now, when I look at all these numbers here, and all these units, some of them cancel out. So these two cancel out. And these two cancel out. And the only thing that's left is liters, which is good because we're trying to solve for a volume. If I'm solving for volume, the volume needs to have volume units, which is liters. So now I can punch this in the calculator. All these numbers. And I got 2.41 liters. After I take account for sig figs, because they all have 3 sig figs. So that's how we do a combined gas law problem. And you use the combined gas law when you have all 3 values present. Pressure, volume, and temperature. Now, if you don't have all 3 volumes present, or... not volumes, I'm sorry, all 3 values present. So if you don't have, like, say, temperature, or something like that, then you could just use Boyles Law, which is just the P1 V1 equals P2 V2. Or what you can do is you can use the combined gas law and just eliminate any variables that aren't present, and you'll get the other ones. So for instance, if I go back here... there it is. If I go back here and I say P1 V1... if one of my variables just isn't present, or I say, like, something like this, T is constant. What that means is that the variable that is mentioned doesn't change. So if this number is the same as this number, then it's like I'm doing the same thing on both sides already. If I'm dividing by 300 Kelvin on both sides, it's the same effect. And so if I have a constant value, what I do is I just get rid of them. And then they don't show up in the equation. So anything that is written as this is constant, you don't need to put it in the equation, and then there's your new formula. That's just Boyles Law. So you can either remember the formulas and go find the one you want, or you can just remember the combined gas law, and then X out the variables that are constants, because they don't show up. They're constant, they just get canceled out. So that is a math trick that you can do. All right. The last gas law that we have is called the ideal gas law. And the ideal gas law is useful for relating all the properties together in a state that is not before-after. It's just a current state sort of thing. And so this links the 4 properties that we talked about at the start. Pressure, volume, temperature, and then also number. And the formula for the ideal gas law is this. PV equals nRT. Or PIV-NERT, as chemists like to call it. Now, you've seen PV, N, and T, but R is that constant again. So we were drawing K over and over again, because K is just what's used for constant, because I guess C was already used for something or whatever. But R is the special constant specifically for gases, and it has this value, 0.08206 liters atmospheres per mole Kelvin. And those are a lot of ridiculous units that you've probably never seen something written like that before. And that looks like this. Why do we have all those units in our constant? The answer is, it's set up this way so that all of the units cancel out, leaving only the unit that you want to solve for. So if P is in atmospheres, and V is in liters, and N is in moles, and T is in Kelvin, and you know all of them except for one, the thing that is left over will be the unit that's left. Now, how do you know when to use this formula? The way that you use the ideal gas law is you use it when there are no after situation variables present. So if you only have one volume, and you only have one temperature, and only one pressure, then you use the ideal gas law. But if it looks like, oh, I have this situation, and then after now it looks like this, you don't use the ideal gas law. So it will be up to you to determine which time to use which formula. I hit the wrong button there, sorry. So the rest of the period, what we're going to do is we're just going to do practice problems using the gas laws so that you can become more familiar on how to use these, because the algebra is not difficult here, but what's tricky is how do I process all this information? Because I'm just throwing a bunch of numbers and words at you. How do I know what to do? And the way to get around that problem is to do a bunch of these. So that's what we're going to do. So this first problem that I'm going to have you do, I'm actually going to guide you for a second. So first I'm going to give you a hint. We do have to use this equation. But I have this sentence right here. Is there a part of the ideal gas law that gives you grams as an answer? Or a unit? Any idea? Which of those units, variables, P, V, N, R, or T, tells you grams? Now, none might be the correct answer. But it might not be. I might be trying to just get you to think here. So what does N tell us? N tells you what unit? What are the units of N? You're really close. So N isn't the number of particles, because that would be Avogadro's number, right? So N is actually moles. But you're exactly right that you can turn that into grams. And so you got to remember how to do that from chapter 6 to solve this problem. So first, calculate the number of moles of gas, and then calculate the mass of the gas using that. So I'm going to give you 5 minutes to try this problem. Type your answer in the chat when you are ready, and we'll go over the answer at that time. how are we doing? Do we have an answer? It should be a small number, less than 1. That's the right answer. Very good. How about other students that are working on this? Do you need more time? Should we go over the answer? What would you like me to do? All right. Let's go over the answer then. We'll go here. Oops, I don't have all the stuff on the screen. All right, a balloon contains helium. Oh, I missed the thing there. There we go. And so, according to the problem statement, we know that it is heated to 425 Kelvin. So we know that this is the temperature. At atmospheric pressure, so its pressure is 1 atm. And that the volume of the balloon is 0.925 liters. And so the question is asking, how many grams are in the balloon? Well, we don't know how many moles are in the balloon here. But once I know the number of moles in the balloon, I could then turn it into grams by using dimensional analysis that we did in Chapter 6. So let's do that. So let's do PV equals nRT. I'm going to solve for n. So when I do n, that would require me to divide both sides by RT, so these cancel out. N is just PV over RT. I can now plug in the numbers. So P is 1 atmosphere. V is 0.925. That's not 5. Oh, everything is terrible. 0.925 liters. There we go. Ooh, that was a really long division bar. R is the gas constant, and it's always the same units, and it's always the same number. And then T is the temperature. All right, so now it's just a matter of what cancels out. So atmospheres show up twice, liters show up twice, Kelvin shows up twice. The only thing that's left is moles, so that'll work its way to the top. Remember how we talked about how units on the bottom of a fraction, in the bottom of a fraction, resolve. 1 over 1 over something is the same as something. And you can check that out in the Chapter 2 lectures when we did the discussion on density, I believe. And all the other ones, you should be able to see how those cancel out. So that means that n is going to be... What did I get when I did this? 0.0... Oh, my calculator just turned off in front of me. 0.0265. So that's the number of moles. Now, in order to turn that into grams, we need to know what the gas is. And it says a balloon containing helium. So that must be moles of helium. Now what we can do is, for the last step here, we can say, oh, I've got moles of helium. And I know how many grams there are in a mole of helium, because that's on the periodic table. 4 point... I can't read the number. 0026. And so I times those together. I get 0.10616, which is too many sig figs. So we'll just take the first 3. There you go. Yeah, don't forget the ideal gas constant. You'll always need to have that number. So whenever you take the Chapter 7 quiz or Exam 2 or the final, make sure you have that constant just somewhere. Like if you're writing a table of formulas and constants, that's one to keep handy too, because the gas constant will come up. All right. So we'll go back here. So let's give you another problem here. For this problem, I have a gas that contains, or a piston that contains a gas. Here's its volume in atmospheres and pressure. I'm just misspeaking here. Here's its volume and pressure and temperature. Then I'm going to compress the piston. What is the temperature after the compression if these are all the variables that are involved? So I'll give you 5 minutes to try this one. Then we'll go over the answer, and then I think that's it for today because we're out of time. So give this one a shot, and we'll see if you can get the answer. So we're running out of time here, unfortunately, so I want to go over the answer before it gets too late. That answer looks good to me. I don't know what the answer is without having done it yet, but it should get hotter just because you're compressing it. And the pressure is increasing. So let's do this. Oh, that worked pretty good. There we go. Let me get the pen. All right, so what do we got here? We've got pressure, volume, and temperature. Initial and final. And so the volume initially is 0.200 liters, 1 atm, 273 Kelvin. So this could be like an engine piston on like a very cold day before it's ignited. And then once the ignition turns on and the gas is compressed, is that the right volume? Yeah. Then it starts to heat up. You don't have to memorize these formulas. Again, you could use these notes on your exam like you've always have. But knowing how to manipulate the formulas is going to be very important, and that's something you want to be able to do relatively quickly. So I'm going to move T2 up to the top here. And then I'm just going to solve for T2 by moving these down and this one up. I'm just skipping the algebra here because we're short on time. And now I can't see the numbers. Now you can't see the numbers. Let's do this. All right, so that's going to equal, so P2 was 2.75 atm. V2 was 0.0950 liters. T1, 273 Kelvin. P1 was 1 atm. And V1 was 0.2 liters. And there is no R in here, so we don't include it. When I punch all that in the calculator, 75.0950273.2. I got 357 Kelvin. So your answer is close enough. I would accept both. And I think that does it. So let me go back to the regular slide here. And then I have the extra practice problem. So there's more of these that you want to try here for sure. And there's the homework practice. So there's lots of homework practice for this section. That's all the time that we have for gas laws. We're going to do intermolecular forces on Thursday, along with evaporation and cooling and phase changes. So please work on those problems between now and then. I want to thank everybody for coming out tonight. Make sure that you tune in for tomorrow's lecture because we're going to cover some content that we don't normally get to cover in much depth. And it's just something that I find interesting. So we're going to be covering dialysis, which is important if you go into like the kidney health sort of field, and also nuclear medicine, which is just generally important because everybody hears the word radiation and they freak out, and it's actually not that bad. Mostly because if you look around your room, there's radiation all around you. We're going to talk about that in more detail tomorrow. But thanks for coming out to the lecture tonight. Hope everyone has a wonderful evening. Stay safe, stay healthy, stay at home.